Hi there. So welcome to part 2B of homework 2 for computational methods. Today we're going to be talking about how to explain and implement Newton's method for finding the root of a vector of any dimension. So the reason why that's different than what we did in part 2A is because in part 2A, the one we solved for was a one-dimensional function with one variable, one equation. But in this one, well, there might be more equations, there might be more variables we're going to be looking at. So what we're going to do is we're going to implement a modified Newton's method. So if our original Newton's method worked by calculating the next x value to test by basically taking our first x value and then subtracting it by the difference of the function solved for at that x value divided by its derivative. Well, when we're working with more than one equation, more than one variable, we can't use a simple derivative anymore. What we have to use is we have to use a Jacobian. And Jacobian as a refresher from homework 1 is an array of partial derivatives for each function you give it. So here we go. So we want to use, so this is in the Newton's method Wikipedia page. And this talks about, well, what do you do if you have a system of equations? What do is you solve for k equations by so you give it vectors instead of scalars. Instead of dividing by its derivative, you have to multiply by the inverse of its Jacobian matrix. So this is the expression that we're going to give it right here. So let's go ahead and do it. So let's define this as Newton n, and give it a function. And instead of this will look pretty similar to the previous ones, except our x naught that we're going to give it is not a scalar anymore. It's not just a single value. In this case, it's going to be a vector. And our function is going to be all of our functions that we're going to need. So we have f x naught, then we have our max iteration, so 200, and our tolerance is equal to 1e negative 10. Okay. Now, first things first, we're actually going to solve for our Jacobian. So let's do f for Jacobian, or that for Jacobian, equals our Jacobian of f solved for x0. Okay. Now let's say that our f0 equals f of x0. So same process we did before. And we're going to make an xy list. Do we want to do that? No, because I don't think we can do that, because in this case, f0, x0, and x1 are all vectors. And they're all matrices, they're all vectors, and so it might not work the way we want it to. So let's jump into our for loop. And what do we want? So we want to do, this is where we're going to apply this here. So you have x1 equals, that's going to be x0 minus the inverse of the Jacobian times the function solve for at x0. So it's going to be x0 minus and once we have the inverse of the Jacobian, then we're going to multiply it by f of 0. But since they're both matrices, we can't just do a simple multiplication. What we'll have to do is we'll actually have to do a matrix multiplication, which in Python you have to use the add symbol for that. So we have times f0. Okay. Then what we want after we have that, then we'll do f1 equals our series of functions by our new x1. Our series of functions multiplied by our new vector. Then we'll do less than our tolerance. Then we break as usual. Then we're going to reset our variables for the next iteration, x1 comma f1. And the existing x1 and f1 will get overwritten when we jump back through this for loop. Okay, so let's return. And return x1, f1. Okay, so let's see if that runs. Okay, so it ran, but normally when you use one of these, it'll tell you what, kind of like highlighting this Jacobian, it'll tell you what's going on. So that tells me that I probably have this wrong. So you might have to do dot, and now dot in. See if I got that right. Aha. So what this does, yes. Okay. And since we're looking at a matrix of our system of equations, we actually have to take the norm of it instead of just the absolute value like we could if it was one-dimensional. So this is our function for our Newton's root finder algorithm. If we use more than one equation, more than one variable. So if it's a vector of n dimensions. And as you can see, the way this is set up, it'll work no matter how many dimensions you put into it. So that's all for part 2. So join me in part 2C, where we implement Boyden's method with step size adjustment and the inversion of Jacobian. And we'll explain what Boyden's method is and more when we get there. So join me in part 2C. Thank you.